when I contacted Lee to say, hey, we're not done with the Crater Lake field trip because Clark would like us to recap the trip and the slides in some fashion at the banquet, Lee's reaction was, holy cow, there could be volcanologists in that audience and we'll be unmasked as imposters. It's always great to go on a field trip with someone who is an expert in the area, who's been studying it for decades and knows every rock and stone. And that's not the case here. Neither of us were experts on Crater Lake, but I had been there and I loved it and loved the geology and had a great interest in it and gained a lot of confidence from having been on one of the GSOC field trips that I didn't have to be an expert. So both of us did a bunch of reading up. It helped that Lee had a background in volcanology for his PhD on Mount St. Helens. And between the two of us, we were able to figure out enough to pull together a trip and answer most of the questions that came up from the great participants. So we're going to go run through a little background here on volcanology and Crater Lake, and we'd be thrilled to take your questions and comments at the end. So we'll talk about the geologic setting for Crater Lake, and Lee's going to talk about how volcanoes behave and some of the processes involved. I'll tell you a little bit about the history of Mount Mazama and the geology there, and then we'll wrap up with some highlights of the field trip. Okay? Right, we have to acknowledge important people who made the field trip possible. And so shown there in the top picture is Charles Bacon, who is the current sort of world authority on Crater Lake volcanology. He's been at the USGS for 30 years. He did the definitive modern map of the whole region, and he used his expertise in geochemistry to understand the composition and the age of all the rocks that are on the map and put the whole picture together with all of the right dates for all the rocks and deposits. He hosted an international group of volcanologists in 2017 and took them all around Crater Lake and produced a fantastic field guide, which was our starting point for the trip. And then he coached me over the phone and Zoom on what we should and shouldn't do and look at, and answered a lot of good technical questions. He even gave us 10 free maps, which we distributed to some of the participants. Of course, Carol, as with any field trip, a pivotal contributor to organizing the trip and making sure it worked smoothly while we were there, and then writing a beautiful follow-up summary, which was in some ways even better than it was. Barb, treasurer, helped organize, and then we had Larry and Sheila here. Both were terrific and safe van drivers, because we had to use vans because we were in a national park and we couldn't have a huge caravan of 10 cars tootling around because we didn't have space to park them. There we are. We have a few attendees here today who were on the trip. We had a really bright group thanks to Carol's safety planning. We had vests because we were working along the roadside, and here we are standing on the north side of the crater, looking back at the crater walls on the south side. And I guess by way of introduction, something that's really exciting and interesting about Crater Lake is, well, number one, it's a really recent explosion. So we have not had a glaciation since it exploded, and so we have great preservation of what happened there when it did explode. And because there's a crater, we have these fantastic caldera walls, so we're getting cross sections in 360 degrees of the entire mountain. The whole volcano is now visible to us in the crater walls, and the work by Dr. Bacon and predecessors to scale those walls and map them has given us some great guides to what happened there in the past. And then we could drive the crater rim and look into the crater, but also at the deposits along the road to get a really fantastic view of a modern Quaternary volcano, how it was built, what happened when it exploded, and what happened after it blew its top and sank into the ground. We did have sunny weather, which was good. It was triple digits both days, so it was way too hot to be standing by the side of an asphalt road. But we managed, and there was not too much complaining. I think most of you, if you've been to events and any of these talks that have gone on here for a while, or if you've watched any one of a bunch of different YouTube videos on the Pacific Northwest, you're familiar with the geology, but I will orient you briefly. I'll start with the map on the right. So the map there is stretching from Canada in the north. You can probably see the outline of Washington State and Oregon and California out to the west. In the Pacific Ocean, we have a couple of plates which are being subducted beneath Oregon. And there's a nice cross-section that appears in Marley Miller's Geology of Oregon, which is shown on the bottom left there, which shows that descending Juan de Fuca plate, which is going beneath all of these accreted terrains, which make up most of Oregon all the way back to the Idaho border, the so-called Walla Walla, Franciscan, Silesia, underpinning everything here. And then Juan de Fuca is scraping off sediments, making the coastal range. We have a bit of a back arc basin there with the Willamette Valley full of Columbia River basalts. And then this subduction has gone on for about 40 million years. And so there's a really old set of volcanoes called the Western Cascades. And just very recently, during the past couple million years, we see preservation of the current set of volcanoes in the so-called High Cascades, which is the current 12 or so active volcanoes that stretch from Lassen Peak down there in California right up to Mount Garibaldi and beyond in Canada. That's about 1,000 kilometers of cascades, volcanic activity in our backyard today, and great for us to be out and have the opportunity to study some of that. What was shown on the right there is just a USGS bit of topography, which I thought further illustrated some of those elements, so that you can pretty clearly see the low part, that's the Willamette Valley. You can see the high of the coastal ranges there. This is, of course, mostly Oregon coast here, California border there. And then high points for Mount Shasta. Crater Lake is just about there, Sisters, and all of the familiar peaks that we know and love and see out our windows day to day. There is a terrific figure that has been repeated in a lot of places, and I really don't know who made it first. If somebody knows, please mention it. But what's shown here is all of these volcanoes from Lassen Peak up to Mount Baker, from south to north. And then what we're showing is their activity just over the last 4,000 years. And so every time there was an eruption, there's a little volcano there. And this is pretty interesting because it shows, for example, a lot of activity in the north the last 4,000 years, sort of a gap in activity in the central area, and quite a bit of activity in the south. You can also see Mount Shasta has been very active. Maybe Mount Shasta is going to erupt again, probably. Wow, Mount St. Helens has been really, really active. Maybe that'll do something again if it's not finished after May 18th, 1980. Crater Lake, of course, did its thing 7,700 years ago and has gone to bed and has not erupted here. So just a little bit of context for the Cascades and how Crater Lake fits in there. I'm now going to pass over to Lee to talk a little bit more about some work we've actually done after the field trip. Lee and Randy Humiston and I trying to understand a little bit more about how the Cascades behave and what goes on with magma chambers. And he'll also talk about volcanic processes. I should also say that I couldn't have done this field trip without Lee. I wouldn't have had the nerve to do it, so I really appreciate him and all his contributions to the planning and the execution of the trip.
I've seen that Ben Sloan mischievous look before, and I was dreading the worst there. After the field trip, I read a paper by Wes Hildreth of the USGS Geological Survey he did in 2007 on basically the volcanism of the Cascades, and it reminded me of something that since I'd done my PhD like 35 years earlier, I'd kind of lost track of, because when you think of the Cascades, you tend to think of the snow-clad stratovolcanoes, because obviously they're so visible. But that's not really the Cascades. They're much, much more than that. And this paper brought that back to me. I mean, they basically are, let's see, more than 2,000 independent volcanoes. A lot of volcanoes. So, usually they're, the little white triangles are the stratovolcanoes. The red are where you have fields of extra volcanoes. So the extra volcanoes are generally spatially associated with the stratovolcanoes, but there's so much more. And I'd completely forgotten about that. So for instance, if you're down in the Bend area, there's just a zone from Newberry over to the Sisters. It's just pretty much solid volcanoes. And you can see, actually to take it back to the Crater Lake area, all these, here's the crater itself right there. All these other little dots are small volcanoes. And it gives you kind of a sense of how things work. You've got that main stratovolcano that was Mount Mazama, but all these other volcanoes associated with it as well. And that's really the true Cascades, and I just wanted to remind myself of that, and you as well. There's a lot more to the story on that map, but that's really all I wanted to cover in this case. Oh, the one other thing I'll say is, you have the main arc itself, but one of the things I tended to forget about is you have both fore-arc volcanoes and back-arc volcanoes. And some of them are fairly significant. Rainier is generally considered a fore-arc volcano, as is Mount St. Helens, as are the boring volcanics right around Portland. And then to me, the most prominent back-arc ones are the Simcoe Mountains, Newberry, and Medicine Lake down near Mount Shasta, all of which are significant, mostly basaltic eruptive centers that are related to the basin and range, particularly in the south. So it's a lot more complicated cascade arc than you might normally think of. Oh, okay, that seems backward to me. So I just wanted to go back over the basics of explosive volcanic eruptions, because the stratovolcanoes that we have in the Cascades tend to have a lot of explosive eruptions, as opposed, say, to the volcanoes in Hawaii that don't. So why is that? This is kind of pretty familiar stuff for a lot of you. We have a range of compositions of volcanic rocks, from rhyolite to dacite, andesite, and basalt. And those vary in silicon content from 70 to about 50%. That'll be important in a minute. The eruption temperatures vary from cooler at the rhyolite end to hotter at the basaltic end. You take those two things together, and what that means is that at the rhyolitic end, and this is the end that our volcanoes, our stratovolcanoes tend to be rhyolite and dacite. When you combine these two things together, they are very high viscosity. You don't need to understand what that number is, except it's about 10 million. Whereas a basaltic lava is only about 500. So 10 million versus 500. Very viscous versus not very viscous at all. Because it's cooler and the silica creates a lot of viscosity. So why does that matter? There's one other factor to bring into this. The gas content tends to be much higher at this end than it does at that end. Now you take viscosity and gas together, and that dictates how explosive the eruptions are, because it's a gas that explodes. And so here's a really simple idea, diagrammatic idea. You've got a magma here, and as it comes up and pressure decreases, you've got liquid in the magma that then exsolves out as gas and creates gas bubbles. The more gas you have, the more bubbles. But the other factor is, the more viscous your magma, as those bubbles form, they try to get bigger, but if the magma is very viscous, they can't. And so in a rhyolitic magma, where you're very viscous, the bubble tries to grow, it can't, so it maintains a very high pressure in that bubble. Whereas if you have a basalt, you have less bubbles, and then as it comes up, it can actually grow, and it can release a little of that pressure. And so the net result of that is, when the basaltic magma comes up, it's not really all that explosive. There's less gas, there's not as much pressure. It comes up, that pressure forces the magma up hundreds to a few thousand feet up in the air, comes back down, and generally comes down as lava flows or like cinder. All right? But in our stratovolcanoes, that tend to be more at this end, you've got a lot more gas, very high pressure. When it comes up, it just basically fragments the magma completely into ash and pumice, blows it 50,000 feet up into the air. and you get these extremely explosive eruptions. So that's why we tend to get those in our volcanoes. And so you end up with more lava flows at the basaltic end and what we call pyroclastic deposits in the more explosive eruptions. Pyroclastic just meaning you've blown the magma into fragments and you have these clasts and grains of ash that come down to create a pyro, which is fire, and clastic, which is all those clasts, those kinds of deposits. All right? Okay, so what do you end up with in our eruptions? Well, you get, as you might expect with something like that, you get huge ash columns. One of my particular favorite products out of a volcanic eruption are pyroclastic flows. They're really dramatic features. This is a pyroclastic flow at Mount St. Helens in one of the smaller eruptions. But what basically happens with a pyroclastic flow, there are a bunch of ways you can form them. But let's take this first one. When you first start the eruption, it's really got a lot of power, a lot of explosive power. It tends to send ash airborne and then off way over there. And then later, as you use up a lot of that gas that you saw in that diagram, the explosivity comes down a bit, and you can't fire that stuff way off this way. It goes up, runs out of steam, as it were, and then falls back to the ground and flows down the ground as this pyroclastic cloud of ash and pumice flowing along the ground as a dense layer, running at like 65 miles an hour and really hot. And that's what this thing is, flowing down across the ground. There's the front of it, and it's kicking up ash behind it. They're extremely deadly. They move fast, they're very hot. If a person gets caught in one of those, they breathe in that ash, and it's very hot, and it actually causes their lungs to vaporize, and they literally explode. So there's something you want to avoid, generally speaking. All right, so there are a lot of ways of doing this. You can go up, fall back down again. This is called a column collapse. And because you get up real high and fall back down there really fast, you can just come up and basically boil out of the volcano and flow down the sides. You can have a dome that has a crust over the top of it, but it's still hot and molten in the inside. The crust fails and the thing can come down as a dome collapse. Or like you had at St. Helens, you can actually blast out the side as a lateral blast. All these are pyroclastic clouds, very, very dangerous features. All right, my personal favorite, mud flows. Mud flows occur on volcanoes anywhere you got water. That's the essential ingredient of a mud flow. It's a mixture of ash, rock, pumice, and water. So the key ingredient is water. You get them a lot on tropical volcanoes. In Indonesia, they're called lahars. But you get them a lot on tropical volcanoes because you have a lot of water around, rain and so on and so forth. On our volcanoes, the water comes, generally speaking, in the form of snow and ice. So one of the key to getting lahars or mud flows to form on our volcanoes is taking all that hot rock and ash, mixing it with snow and ice, melting it fast, and generating a mud flow. So I looked at two of them on the Toutle River. This one is actually a nice example of one coming down a valley in Indonesia, so that's what they look like when they're moving. And this is one that, what it looks like after it gets done. And what I love about this is what I used to call the tacky Tudor house on the Toutle River. And what I love about this is this thing belongs back there attached to the house that way. So I have to do it this way, but started that way, attached to that house, the mud flow took it apart and brought it this way. And that happened because mud flows are really smart, and that mud flow figured out that those two halves of the house were connected by a 2x10 board and wires and plumbing, and that was it. I don't know why they built the house that way, but mud flow figured that out and said, well, I can take care of that. And brought this thing and put it over there. But that's what mud flows can do. So that particular mud flow wiped out about 65 houses in various dramatic fashions like that, quite a few bridges and so on. All right, and the last thing, since this is a crater lake thing, the last thing, of course, is calderas. Now, one thing that's interesting about the Cascades is there actually aren't that many calderas in the Cascades. It's unusually low number, but it just happens to have one of the most dramatic of them of all, which is Mount Mazama and Crater Lake. And so the formation is pretty straightforward, but you start by building a magma chamber. So the magma chamber in Crater Lake built over the course of about 35,000 years. And it got quite big. That's requirement number one. You have to have a big chamber. then you have to evacuate most of that chamber. So you have to have a big eruption. So you have a big eruption, you basically get rid of all the support for the rocks above it. The rocks just fall down in, and you create your caldera. And then usually what happens after that is you'll have one last phase, which Crater Lake has, of minor eruptions after that. So that's Caldera Formation. It's a pretty standard process, but nonetheless quite dramatic. So I think, Ben, you're up.
Okay, let's talk about Crater Lake specifically. A little bit about the historical exploration, discovery, scientific activity at Crater Lake. We don't have a written history of what native peoples thought of Crater Lake. Orally, we know that it was considered a sacred place. And there were some stories about different gods and activities that occurred there in the water, in the sky, on the mountains. The Europeans arrived in 1853. This gentleman, John Hillman, discovered the crater while prospecting for gold. And then this gentleman, William Gladstone Steele, was the early champion of Crater Lake and convinced President Roosevelt to turn it into a national park, one of the first 5 national parks in the US, 1902. And immediately funds were brought in to start building infrastructure there, roads, and of course the marvelous hotel there at the rim. The USGS, this is amazing. Here they are. USGS was founded in 1879. Before it was a park, there they were, 1885, out in their boat. Probably a few trips back to shore to get more string or wire, or however they were measuring the depth of the lake. And no doubt shocked and surprised to find out that it was almost 2,000 feet deep. A beautiful map shown there. Already in 1902, the USGS made a pretty good regional map of all of the geology that they could map in the area with the tools available to them around the turn of the previous century. Then a huge leap forward when a volcanologist professor at UC Berkeley, Howell Williams, did an extensive study of every outcrop in the caldera and around the park, and all the mineralogy, named all the rocks, all the formations, and did a huge, beautiful write-up that was published in 1942. He was still around Berkeley when Charles Bacon showed up to do his dissertation in the 1980s, and as I said before, what Bacon did then was bring all of the geochemistry, which then gave all the specific compositions of all the rocks, and age dated everything, so not just relative age, but absolute age, so we knew within in some cases a few hundred years the exact age of all these deposits. And of course, lots of other people have worked on it. These are the main contributions historically. Okay, we, like every GSOC trip, there was a fantastic mix of participants who knew lots about geology and even volcanology to almost nothing. And so Lee and I attempted to summarize things in a way that would be interesting and easy to understand. And this is the summary of what happened at Mount Mazama. So we built a big mountain, then we got ready to explode, then it exploded, and then there was a little bit left over. So the four basic stages that we've defined here is 1, 2, 3, 4. So the first stage was from 400,000 years ago to about 30,000 years ago. And that was building the volcano out of layers of mostly andesite and quite a bit of dacite as well. Around, Lee mentioned, around 35,000 years ago, the big main magma chambers started to form. And that's when the behavior of the volcano changed a little bit, and we had actually less activity, but we did have some big dacite domes that formed. 7,700 years ago, everything exploded and went all over the Pacific Northwest and the globe eventually, and then collapsed into the caldera. And we had a little bit of activity following that, but not very much, because most of the energy was shot at that point. So just stepping through those one by one, stage 1, the construction of a big composite volcano. Howell Williams, who I mentioned a moment ago, published in his 1942 volume, a comparison of the flanks of Mount Mazama as they are preserved today to other volcanoes in the Cascades. And just based on the geometry there, he concluded that the volcano looked similar to Mount Adams and must have been about 12,000 feet high. So today, we're at about 8,000 feet on the Caldera Rim, so we've removed quite a bit of mountain has disappeared. Most of it sunk into the ground. The eruptions there were relatively thin-bedded. I'll show you pictures of that, but we had 400,000 years of sort of sporadic eruptions of modest quantities of andesite and dacite that built up this lovely volcano. And we know from its height, 12,000 feet, that it would have been glaciated, and we see good evidence of glacial valleys around what's left of the caldera today. Stage two. Stage two is kind of weird, but as the volcano got ready to explode, it began to behave strangely. And one thing it did was emplace some dacite domes that were very viscous. So instead of andesite coming out, running across the ground and helping build the volcano, we had these plugs of very, very viscous dacite, which came up and didn't flow very far at all and got very thick, right close to the volcano. So I want to point out, I think if this is clear from the back, but here we're looking at a feature along the wall of the caldera. So this is about 2,000 feet of relief. This is a feature called Lau Rock, which is probably the most prominent feature on the caldera walls. And what you should be able to see is that under Lau Rock, we have a whole bunch of relatively thin, these are a few meters thick to maybe 10 meters thick, old 70, 80, 100,000-year-old andesites, which built up over a great period of time. And then all of a sudden, we got almost 1,000 feet of rhyodacite all at once that was so viscous it couldn't go very far, and it could build up a massive thickness right on the side of our volcano. And this one is strange because it actually is, Bacon has dated it now, it's just 200 years before the final eruption. So just before everything cut loose, we had a big glob of sticky, viscous lava came out and stuck to the side of the volcano. There's a second one over at Cleetwood Cove, which we looked at on the field trip, which basically predated the eruption by less than 100 years and was still hot when the volcano erupted. So, stage three, the big kapow. These graphics are from Bacon and Wright in that field guide from 2017. And the big eruption actually had two parts to it. And what we call the single vent phase, which was the first phase. So we had near the center of what's the caldera today, just on the north side, we started a huge eruption with a giant ash cloud that was going 50,000 feet into the air, and the wind was blowing toward the northeast because we see that ash preserved on the northeast side of the volcano and all the way to Greenland. The next thing that happened was that there was enough magma removed that we started the collapse of the top of the Mount Mazama into the volcano. And that happened with what's thought to be a ring vent. So this phase two is the ring vent phase. So we had a whole ring of vents in a circle in what's the center of the current day caldera. And the whole mountain pushed down and forced out all of the magma, which in that case went in every direction, as evidenced by the mapping around the caldera today. And Bacon and Wright have a beautiful, somewhat complicated depiction of the single vent phase, the ring vent phase, and what we're likely to see during those phases close to the caldera rim, 15 kilometers out and 30 kilometers out. So that's the high column from the single vent phase. That column collapsed, and we probably had pyroclastic flows, ignimbrites. Then we had quite a dramatic ring vent phase were a whole lot more material with a lot of lithic fragments being blasted out as the top of the mountain descended into the ground. Right. And then almost as an afterthought, there are some features mapped mostly since 2000 or so, when the USGS got funding to do 3D sonar of the Caldera floor. They identified these features that were developed in the first couple hundred years after the eruption, the most prominent being the one that peaks up above the lake level, and that's Wizard Island. And since then, things have been pretty quiet and probably will remain that way. Back to Lee to talk a little more in specifics and volcanological terms about how the eruptions behaved.
And we're running out of time, so I'll do this pretty quickly. But one of the interesting things about all those eruptive stages is how they moved around the volcano with time. So in the early stage, the first things to come out, so stage one, which was the construction of that composite volcanic edifice, it really started primarily down where these blue colored eruption flags are right here. And then with time, it shifted to the north primarily where these yellow flags are. So the main Mount Mazama, that 12,000 foot feature, started as a feature in the south and then added another feature up in the north to create the whole cone. Once it was done with that, then that gave us the cone that we started with. Stage two, we had pre-climatic eruptions that Ben just mentioned. Those are these orange flags right here, including Lau Rock right there, which is that thing that happened just 200 years before. So I kind of think of Lau Rock as getting the plug of really viscous magma out of the way so the whole thing could blow out. I don't know if that's true or not, but it's one way of thinking about it. So we had that, and then third stage then was the climactic, as he said, starting right over there in a single vent and then moving to the ring vent stage, and then finally in gray the flags of the post vents. So starting south to north, followed by north, ultimately shifting into the main magma chamber underneath the center. So it's a pretty complex history. Do you want to talk about this or you want me to? So, basically, again, Ben's already pretty well covered this. The idea that you just see a beautiful exposure in the sides of the caldera of the history. So here, most of the sides of the history of that early stage one construction of the volcano, generally basaltic andesites or andesites, relatively thin-bedded lava flows. All the lower flanks of that, in some cases all the way up the Watchman and Hillman Peak, are all part of that early stage one construction, these dikes. And then stage two is visible right here. That's Lau Rock, that big plug of very viscous dacite that came in just before the climactic eruption. Stage three, which is the climactic eruption, is barely visible in this picture because it mostly blew all over elsewhere and down the flanks as pyroclastic flows, but it's visible as a little bit of pumice fall right there up on top. And then the final stage four would be Wizard Island right there. Here is a summary of all the stops we did, starting from 1 to 13 over the course of 2 days. One of my favorite, and it just doesn't show up very well in this picture, but if you ever go to Crater Lake, absolutely go down to Annie Creek, because what's really cool, you can barely see it, these are the pyroclastic flows that came out during the climactic eruption. The bottom is very light tan color, and the top is very gray. And it's exactly the reverse of what was actually in the magma chamber. In the magma chamber, what you had was a primarily rhyodacite magma chamber, but in that magma chamber, stuff was settling out of the magma, mostly dark mafic minerals. So, pyroxenes and hornblends and so on. They're settling down to the bottom. And then when the eruption came out, the top came out first. That's your brown rhyodacite. And then it just works its way down until it gets into that mush at the bottom, which is the dark gray to black minerals. And you see that totally flipped over. Oh, you little. You see that totally flipped over in this outcrop where the first thing to come out is at the bottom and the last thing to come out is at the top. That is a very rare outcrop. You just don't see that very often. So if you're ever at Crater Lake, remember Annie Creek. It's right on the road just outside of the park, and go down and see that because it's a really extraordinary opportunity to see that. I'm not going to talk in detail about a lot of the other stops, but most of them were really good. Some of them were a little bit iffy, but it was a great trip. And with that, we will say thank you. We have a bit of time, so if anybody wants to, says I'm supposed to stand. What does it think I've been doing? Anyway, all right, so we can take questions.
The second stage was the rhyolitic day site, as you said. Why, I get confused. Why are we talking about levels of magma? I would think the heavier stuff would be at the bottom to begin with the andesite on top of them. But the day site rhyolite erupted before that. I guess I'm confused about why you have a certain composition.
Okay, well, first of all, let's just say that the dacite and the rhyodacite probably comes largely as a mix of magma that has come up and then melted all the rock beneath the volcano in order to make that huge magma chamber. And so when you combine those compositions, what you end up with is primarily a rhyodacite to dacite. All right, so think of the magma chamber down there as rhyodacite to dacite. And then as that magma is starting to cool, crystals form, and the first crystals to form are very mafic, iron-rich and magnesium-rich minerals. And those are heavier than the liquid because they're solid, and they settle down to the bottom and accumulate down at the bottom. So now you've got this layer down here with rhyodacite up above and this layer of mostly iron magnesium mush crystals down at the bottom. When you rub that out, then you take the top off first and you keep working your way down. So the light colored stuff comes out first, flows down the side, deposits, and then right at the end, this dark stuff comes out and forms the capping material at Annie Creek. Does that make sense?
Yes, the andesite went where? Did it just polarized?
So there isn't really per se an andesite. There's just rhyodacite with a mush of crystals down at the bottom that then come out and form the top. Now, if you looked at the composition of that mush of crystals, because it has so much iron and magnesium in it, I think it is basically of andesitic composition, but it's really only because the crystals separated out of the main liquid, and then you pop that out and brought it down. Does that make sense?
Yes, thank you.
Okay.
Do you know what that time interval is between the central vent portion of the climactic eruption and the ring fracture? Is that hours, days, years?
Days. I would get days to weeks, I would guess.
It hasn't been measured, but that's just the idea that this eruption was happening, and based on recent eruptions around the world the last 100 years, things happen over days and weeks.
And that's a guess on our part. I haven't actually read anything where anybody has said that they know what the answer to that question is. Any other questions? Yeah.
Yeah, could you back it up to the photograph of Lau Rock, please? You have
No
the
way.
cross section.
This thing doesn't work right.
There, back right there. You were there a minute ago.
Hold on.
There.
See?
Come on, Ben.
I'll try.
Oh, this thing is.
Okay,
it's fidgeting.
is it occupying a glacial valley there?
Yes.
Okay, you can see that it's looks like it's very deep in the middle there.
And it overflowed to the sides. Yeah. Any other? All right, you're released. No, Clark, where are you? Oh, there. Do you want to wrap it up?
What a relief that they showed up today. Thank you very much. Very enjoyable.